So for the sewer system, the sewer has to do with your wastewater demand. And we all know that wastewater demand varies between 100 liters per second per day to say 150 based on WHO standard. WHO standard says that every human being requires between 100 to 150 liters. Now, Abuja was designed with 100. Some rural areas can go as low as 60, 50. Okay, but then as engineers, one of our job is that we design based on worst case scenario. If you want to design anything, you have to look at the highest probable values, the worst case. Okay, now, if you get the water demand per person per day, you simply multiply it with the number of persons. That will give you the wastewater discharge that they're going to produce. That is also the water demand they require. So based on the law of continuity, what goes in, the what comes out. So AV must be equal to AV. So what you consume, AV of consumption, must be AV of production. So what you take. So if your water demand per day is 100 liters per capita per day, we expect, all things being equal, that you also produce a wastewater that is also 100 liters per capita per day. Then when it comes to storm, now when I say storm, I simply mean rainfall, storm events, rainfall. When I now say storm sewer, then you should be thinking about the sewer that conveys storm, or the sewer that conveys water from rainfall. That is simply what it means. For the sewer, that is now where we use the CIA, where I is now the intensity, the A is now the area of the catchment, C is now what we call runoff coefficient. Runoff coefficient. Why do we talk about C now? In the case of sewer, okay, C is a factor of safety. C will be the factor of safety because after multiplying the specific wastewater demand for one person, multiply by the number of persons, you have to multiply by a safety factor. We are all engineers. There's no engineering design that you do that you don't consider safety factor. This safety factor is what takes care of some unforeseen design lapses or takes care of some escalation of population, escalation of development, change in land use, water losses. You know, there's many uncertainties that an engineer will face. So when you finish your design, there's always the safety factor that we put to multiply so that it will take care of some inconsistencies. So, but in the case of the sewer, the safety factor is defined in the code between 1.3 to 2.5. Just choose based on the number you are designing for. But in the case of storm, your safety factor is going to come from two variables. Those variables are the slope of that area and what we call peak runoff or the degree of paving, the imperviousness of that area. The higher the imperviousness of an area or the higher paved an area is, the more it will contribute to runoff. When we start, you get, I'm just laying the foundation. So that's why many years ago in Abuja, when you go for building approval, if you use interlock or you use mass concrete in your compound, they will ask you to go and provide green areas, greening. What they are trying to achieve is that they were trying to make sure that about 50% of your plot or your property, that the runoff will not be more than 50%. If you pave every area, if you cover every area, infiltration will be low. And that means more runoff will be generated. And that will have an adverse effect on the public storm system. Because the public storm system has been designed in such a way that it will accommodate a certain fraction of all the rainfall that comes to it. So if you now go and do a design where all the waters coming in certain catchments is going to the drain, then you can only imagine how big that drain is meant to be. So to curtail that, approving authorities will always make sure that you have gardens, open spaces, so that there will be a lot of deep, shallow and deep percolation, infiltration, so that it will not be overwhelming for the public sewer. Yeah, I'm recording, sir. Okay, now let's go to what we have. For those of you that have gotten the materials, just be interested in the folders, okay? In the folders, you see I've included a lot of things that will build our capacities beyond this training. Just hold on. I hope you can see my screen. Some of these things are not necessary. I'll send you some of these. These are just I can delete all of these. These are old trainings, example and exercises that we did. The ones that are important to you, I'll let you know. So pay attention to the folders. The folders are where the real thing is. The folders are where everything is. Now, one of the things we're going to be talking about is the Nigerian Code of Practice. The Nigerian Code of Practice has 5 volumes, but the 2 volumes that deals with drainage, I've included it in our folder, in our materials.
I'm sorry, I can't see any folder you're referring to.
What's the name, sir?
Elijah.
Okay, Elijah. Okay. Elijah, pardon me, I guess you have paid.
Confirmed.
Sorry?
Excuse me, I can't see any folder too.
No, all the people that sent me, I think I've shared the materials with us. So if you don't have the folder, that would be quite unfortunate, and I'm sorry about that.
Yes, I paid.
Okay, hold on, let me pause this. So this is example of the highway design manual developed by Koren and the Federal Ministry of Works. Now, what you take away from this highway design manual is the rainfall intensity, what we call the IDF, intensity duration frequency curve, for all the states in Nigeria. Remember, I told us that for storm, you need input of rainfall. You need the input of rainfall. So here, you will see, for instance, this is what you'll be seeing in all of them. So this is Benin Nifo, for instance. This is Benin Nifo. If you go down, you see for other cities. The next one here is Bida. So if you are doing your storm design in a place around Bida, you are expected to go to the highway design manual and pick up the IDF, the rainfall intensity of Bida, okay, for your design. So that is an important document. It's something we should not take for granted. Koren and Koren and Federal Ministry of Works, they built this, and I think it has really solved a lot of problem. It has really helped in a lot of ways. Okay. So now, if you go further, you see other things that you might be news to you, but this is only what is in the highway design manual. So here, you have the rainfall intensity in the vertical axis, and you have the duration in the horizontal axis. And on the diagonal axis, you have the return period of each rain. We'll still come to all those ones. Every rain have a return period. Is it a 1-year rain, 2 years, 5 years, 10 years? The number of years is an indication of the probability of occurrence. The probability of occurrence, which is also a function of the intensity. I always say this, an engineer who designs infrastructure must design based on worst case scenario. This is what I tell my participants. In infrastructure design, it's better to over design than you under design. Under design is dangerous. Over design, okay, you're going to spend a lot of money. You're going to spend extra money. Okay, somebody can tell you are wasteful, but the design will work. But under designing, the design will fail even before it starts working. So if you want to do your design, you need to ask yourself, am I designing against surcharge? Am I designing against flooding? Am I designing for just normal drain? So that is what will determine what line you're going to choose and what rain intensity you're going to anticipate and what is the return period for that rain. So that is that for this. The other folder you have there is the folder that contains the SWMM software. Now, the SWMM software is an open source online software developed by the Environmental Protection Agency of the United States. It's called EPA. If you go to epa.gov, you type SWMM, SWMM, Stormwater Management Model. The software is about 30 years old now, and it's completely free. So if you can't download it here, you can go online and download it. If you lose it, just go to EPA website and you see another one to download. Next is the user manual. I've included a user manual for us. This user manual will help us to learn the software much better than I do. Okay, so it happens that this is a Zoom training, it's an online training, so you might not be able to grasp the whole thing in one day. But if you go through them, the SWMM manual, you can learn and become more proficient in the software. Then the last one is now the big one, which contains the materials for this training. Okay, so if you look at the material for the training, you will see hydraulics, you will see hydrology, you will see sanitary, you will see urban. So there's a whole lot of materials there, But to start this training, I'm going to give us an overview, a short overview of the whole system, okay, of the whole system. So let me open it. So in an urban sewer system, we have hydrology. In hydrology, as I said, this is when you're talking about storm. Then we have the sanitary sewer, which now talks about the anthropogenic human activities. The water you drink, you must reproduce it again as wastewater. So that one, you don't need any type of hydrology. Hydrology is not your business. Then finally, you have the hydraulics. So both of them, you need to do the hydraulics. So let us start with hydrology, for instance. So I'm going to open hydrology. I'm going to be very fast. Today, we are laying the foundation. Tomorrow, we'll start the hands-on design. Some of us are not water from the roots. Some of us didn't study water in our first degree. So it is good for you to, for me to lay a kind of foundation for you, okay? As I said at the beginning, this is a master. They don't offer these courses in the first degree. It's not a first bachelor's thing. It's from the master's level. So let me lay a foundation of that by telling you more about hydrology, telling you something about hydraulics, about sanitary sewer, then wrap it up with hydraulics so that we'll be in a better position. In a sewer system, we have two sewer, or even, two major one. We have the separate one, we have the combined one. What is separate one? Separate one is where you have a separate sewer system going its way. Then you have the storm sewer going differently. The storm sewer is the one we call drain gutter. Sorry to use that word. That's the normal one with the one in front of your house. It can be open drain. It can also be closed drain. Subsurface. But the sanitary can never be subsurface, cannot be open. It just has to be subsurface. And sanitary sewer is usually made of PVC pipe, because the sanitary sewer is between 150 mm to about 450, 600 mm. But the storm sewer is usually from 600 to about 1.5, 2.5, 1.2, even up to 3 meters. I have my friend who did the one for Asaba. He did a storm sewer of 3 meters. Jeffcon Associates for the Asaba State government, Delta State government, because of the problem they are having in Asaba. And that's why today you can see that water is no more a problem in Asaba. But for the sanitary sewer, the volume it is conveying is so small that it's usually PVC pipe buried at a distance of not less than 1.2 meters, depending on the overburden. So the sanitary sewer is influenced by what we call wastewater flow, the flow of wastewater, because sanitary sewer wants to convey your wastewater flow either to your septic tank and soakaway pit or to a centralized wastewater treatment plant. So there's what we call dry weather flow. Dry weather flow is the discharge, the wastewater flow when there is no storm events. It's important. When there's no rain or storm event, I'll be using the terminologies befitting of a water engineers. Pardon me, please, if you don't understand some of them, but I know all of us are all engineers. So if there's no storm events, water that flows in the pipe is called dry weather flow. As the word implies, dry weather means the weather is dry. So if water is flowing when the weather is dry, definitely is a wastewater flow. But then, human error always occur, like we have in Abuja. Due to the sewer system in Abuja, they didn't use PVC at the downstream because of size. So they use some places they use concrete pipes, but good concrete pipes. So over time, they rupture. There is cut, or what do you call it? There is fracture. There is a breakage. There is a failure. And whenever there is storm events or rainfall, infiltration water will pass through those openings and contribute to the discharge in the pipe. So you could see that even though I tell you that storm sewer, sanitary sewer is only from your houses, it's only from your bedroom, from your wash hand basin, from your kitchen, from your toilet, from your bedroom, I might be wrong, because there is also a small function that finds their way into theirs from the storm. Either, so we call them infiltration water. So you add them. That is why you see Q equals DW plus Q arrow DW. So this is runoff due to dry weather flow activity. So it is not like storm, but it is infiltration. So what we normally do is, when you, after designing, you upscale your discharge to accommodate infiltration by a factor of 0.2 to 0.7 per liter per seconds per hectare. I will explain that variable. I will explain that liter per seconds per hectare later. Okay. Why we're always talking about per hectare instead of per capita? It is because we are doing at catchment level. We are assuming there are no houses, so we don't know how number of persons. But then it's a defined catchment based on some level of population density. Okay, so with the population density, we can figure out how many number of persons that can be on that. Okay, every land has what we call the population, the land use, has what we call land use. Land use means, what is this land meant for ab initio? How many people do we anticipate that this land can accommodate? If you go to mainland in Lagos, the land use is very dense. If you go to the island, if you go to the island, the land use is sparse. If you come to Abuja, Wuse, Garki, Maitama, Jabi, all those areas have high density. But if you go to places like Kuje, Gwagwalada, not the Gwagwalada of today, the Gwagwalada of the other day, those days, because Gwagwalada, now, is even highly dense, is dense now. But if you go to places like Kuje, Kayami, Kubwa of those days, when people have not really moved in, so you see that the density is very poor, is low. Okay, so that is for sanitary sewer. When you come to storm sewer is simply runoff. And it is just runoff, stormwater flow. So if you now combine two of them, which is not usually the case in most countries, in most places, 90% of the time, sanitary sewer is separate, storm sewer is separate. But in some advanced countries, they found a way of combining the two. But of course, it cannot apply in Nigeria because of our own cultural preferences and our own technological advancements. So if you combine the two, what they do is that when they combine the two, they monitor it. Once it's raining, they will shut down the wastewater treatment plant, and then the water will go through a bypass into the open stream. As soon as the rain stops and dry water flow starts, they will divert it back to the treatment plant. Okay, so that's that. So back to hydrology. So when we say hydrology, urban hydrology, what do we mean by urban hydrology? Basically, we're talking about precipitation. So precipitation in the form of rain, snow, hail. And we're also talking about formation of runoff. When rain falls, 5 different processes takes place. When rain touches the ground, the first thing that happens is what we call wetting. The second thing that happens is what we call evapotranspiration, which means the plants takes them and then transpire them again through as oxygen. You know, they take carbon monoxide. So in the process, they consume water. If you look at the stoichiometry, you know that when you combine methane with oxygen, you produce CO2 and water. Don't worry about that. We're not in chemistry class now. Now, you have what we call depression storage. Depression storage. Now you now have what we call infiltration. So after infiltration, you now have what we call runoff. So you can see that when rain comes, some will wet, some will go back as evapotranspiration, some will go as depression storage, some will go as infiltration, then only few will come out as runoff. And that is the one we are interested in. So that is that. So you can see here, when rain falls, some will go back as evaporation, some will infiltrate, then some will discharge. So that portion that will discharge, that will cause runoff, is the portion that we're interested in. Rainfall can be described by various variables. Rainfall must have duration in minutes. It must have height or depth in millimeters. It must have intensity, which is combining the millimeter and the intensity, and the duration, sorry. That will give you the intensity. Intensity can be measured in millimeter per minute, millimeter per hour, or millimeter per day. It depends. Then finally, we have what we call frequency. Frequency of occurrence, frequency of rainfall, and what have you. So, in the past, there's a particular formula we use to calculate rainfall intensity. You multiply 166.7 by the intensity, that will give you the rain intensity for 10 minutes at 10 mm. But please don't worry about that now. That formula has been overtaken by new conventions. We'll shortly come to that. So we say that any rain that is less than 7 is about 650 hours per annum is classified. So this is just classification of rain. So we have weak rains, we have moderate rains, and we have heavy rains. So any rain that is more than 21 liters per second per hectare is regarded as heavy rain. Any rain that is less than 7 liters per second per hectare is classified as weak rain. This is what the rainfall intensity looks like. So I've just showed us that before. This is one of the formulas you can use to calculate your rainfall intensity as a function of duration and frequency. So this is the formula, but if you agree with me, engineers, these days we don't no longer talk about formulas in our design. we talk about tables and charts. That is the latest innovation in design. If you want to design anything, get a chart, get a table for it. Once you get your value, you read it off in the chart and the table. So all these formulas have been converted into charts and tables, which I'm going to show us shortly. So every rainfall depends on what we call time factor. Listen to me, gentlemen, this is very interesting. Rain, the rain that will cause havoc or that will cause problem does not usually last for more than 15 minutes. I'll explain to you. We regard it as a 15 minutes rain. And the frequency is the inverse of the return period. So for instance, say in Germany, the rain intensity in Germany is between 190 and 130. In Nigeria, it's almost the same thing. Oh, not quite the same thing. In Nigeria, the boundary conditions, the lower and the upper boundary just changes. For instance, places like Borno have rainfall intensity of about 70 millimeter per hour. While places like Lagos has about 150. That is for a less than 5 years return period. If you're talking about 25-year return period, Lagos is about 200. If you're talking about 100 years, Lagos is 250. But nobody talks about 100 years. The higher number of years, the higher the rainfall intensity. But so averagely, Lagos is 150 millimeter per hour. And Borno is around 70. Then, but there's a place we call Benin Nifo. For reasons I don't know, the rainfall intensity there is hell. It can be like Lagos. The place is not in Lagos, but I don't know, the rainfall is just something else. Okay. So, when, as I've explained this before, when there's precipitation, when there's runoff, what constitutes runoff? Runoff takes place after there's drift, wetting, evapotranspiration, infiltration, diffraction, and then runoff will occur. So if, let's say, 100 liters of water falls from the rain, from the sky, what will contribute to runoff will be between 30% and 50%. Why? Because some will go back, some will infiltrate based on the surface, properties of the surface. If the place is grassed, many will infiltrate. Those that did not infiltrate, the leaf will evapotranspirate them. And then some of them will be wasted, wetting the leaves. And then if the soil is a good sandy soil, then infiltration will be much. At the end of the day, small surface runoff might be less than 10%, 20%. Yes. But if the place is interlocked or mass concrete, then the runoff might be as high as 70, 80%, because it means the whole water will just, none will infiltrate, none will evaporate, none will wet, none will infiltrate, none will cause depression storage. All of them will just go to the drain as runoff. So peak runoff is a dimensionless constant, which means the safety factor is calculated as stormwater runoff over the rainfall intensity. And it depends on the impervious area. It depends on the surface type. It depends on the slope of the surface. It depends on the rainfall intensity. It depends on the type of soil and vegetation. So all these are what we can really understand. Now, my policy in my trainings, in our trainings, is that whenever anything in PowerPoint that we know you can really understand, we don't go talking about them. That's why you have a lot of materials to read. Then, for instance, the roof of your house has 0.95 as peak runoff. Why? It's almost 1. The reason is that all the water that falls on your roof always goes to the drain. So the runoff coefficient is high. The maximum runoff coefficient is 1, but no object has 1 because there will always be losses. Then gravel parts. Gravel part is where you pour gravel on the sandy soil. The runoff coefficient can be as low as 15%, 0.15 to 30%, which means only 30%, only 15 to 30% of the rain that falls in that catchment contributes to runoff. That's what it means. So here is to explain to you that the runoff also depends on the slope. The higher the slope, the higher the runoff. So how do runoff form? Look at these houses here. There are about 8 houses. Rain that falls in these first 2 houses, the runoff will be like this. This water will flow and gets to the second house. The water will increase by this margin. The water will flow again, collect the runoff from these 2 houses. It will increase by this margin. Finally, it will go to the last house. It will now become maximum. That is how runoff occur. So here, this is the impervious area of the house. This one is the sewer. Here, the green area is the garden, and the black center one are the street inlets. So this is a bit simplified, but it's good that you understand it the way it is. So you can see the runoff is rain intensity multiplied by time factor, multiplied by runoff coefficient, multiplied by the catchment area. So after some advancements, the runoff, the rainfall intensity, the rainfall duration are all embedded in the time factor. So you can see that. So take note of this. So you can see this is the general formula. So later on, we will combine these two and it becomes one single factor of safety. Therefore, if you now want to calculate the runoff, it will just be intensity multiplied by the catchment area, which is CIA. So in this case, these two are the C. I is the this, IR, for 15 minutes and for frequency of 1. And then AC is the catchment area you are calculating. I wish I can bring one exercise now and just show us, for instance, how these things are calculated. Well, let's continue. So this is the end of hydrology. Please, any question? Multiply the intensity by the catchment area and multiply by the peak runoff coefficient. That will give you the runoff of that area, the quantity of water that it will contribute. Any question, please? So let's go to sanitary. So in sanitary, the same thing applies. The wastewater flow, the sewage flow is just the wastewater flow plus the infiltration water. I've said it before. But here, storm can be as high as 100 times the dry water flow. Just take note. So for the combined system, it will be the storm system plus the dry water flow. So here, amount of wastewater is called specific wastewater production, represented as W. And it can be written with different units. It can be written as liters per capita per day, liters per hectare per day, liters per production units per day. Somebody should understand that this is for industry. Wastewater generated in an industry is a function of the production unit and not a function of capita or human. The rainfall intensity or the discharge is calculated in liters per hectare per seconds. Every discharge, those that have been in my previous class, is calculated in liters per seconds. Then total discharge can be in liter per seconds, meter cube per seconds, meter cube per hour, meter cube per day, meter cube per annum. Domestic wastewater production across the world. So you can see in most countries in Europe, the amount of wastewater each person produces, which human being produces, is between 120 to about 160, except for US and Japan that has 278 and 295, which I don't know how that is, but I think that's what it is. So the specific production of wastewater depends on the size of settlement, type of building, weight of population, and it's usually between 100 and 250. Please take note, between 100 and 250. Okay, nowadays it's about 130. Why is it going down? It's going down because we keep on producing, developing, more energy efficient water equipment. For instance, the toilet seats that we use today, the one that we used before used to consume about 8 to 13 liters of water. But these days, the one we're using now consumes only 5 liters of water. And if you go to some foreign countries now, their shower have sensor. Once you are there for like 5 minutes, the water will stop. If you touch the sensor, the water will start again. Why? To save water. So you can see that the world is coming up with more and more simple water saving machines and the equipment to save water. So this value will keep going down. Anyway, how do you estimate your Q for your domestic wastewater or for your sewer? Population multiplied by the wastewater demand. That will give you the wastewater flow within 24 hours. So the population multiplied by the specific. Remember, this one is specific wastewater demand or wastewater production. And this one is now the what? Population equivalent. So these are just values to give you an idea of specific wastewater production for Germany. The average is about 150, 130. Okay, for some people 130, for some people 100, for some people 150. But I've told you before, use 100, please. What are the consequences of wastewater and why you should not discharge them into the sewer? Number one, you are not supposed to discharge into the sewer things that can destroy the sewer, hampers operation of the sewer system, diminish the treatment of wastewater treatment plants, impair sludge treatment and disposal, endanger the health of personnel, must not be discharged into the sewer system. And this proposition will hold for waste, hardening substances. So these are the things that can cause problem: oil and fats, aggressive and toxic substances, detergent and disinfectant, animal feces, vapor and gases. So these are the things that we don't want to see in wastewater sewer line. So this is the wastewater production of different industries. Hospitals produce about 250 liters a bed. Swimming pool is between 150 to 180. School children are using between 20 meter cube per people. So you can see that school is the lowest because they don't wash, they don't cook, they don't wash cars, they don't bathe, and what have you. Departmental store, even lower, because people only use it to urinate and wash hand. Restaurant, a bit high. Yeah, brewery, dairy, preserves, and everything. So these are the values. You can read them and understand and follow up. So now, these are just some values. Infiltration water, you can use this. For wastewater, you can use 100, and so on and so forth. That's the end of sanitary sewer. Any question? Any question? Okay, I'm going to continue. Okay, urban drainage. Let's talk about urban drainage, which is just two of them put together. After that, we'll discuss hydraulics. We'll go to simple calculations. Okay, under hydraulics, I think most of these things you can read and understand them. These are the components of a hydraulic system. For the sewer network, you have the gully inlet, you have the pipes, you have the manhole, you have the special buildings. Then you have the pumping station, you have the stormwater tank, you have the filtration structure, and you have the wastewater plant. So this is what the gully inlet look like. All of us know it. Pipes, it can be a closed pipe, it can be a gravity pipe. Cross section, it can be circular, it can be egg, it can be mouth, it can be rectangular. Okay, how do you choose your cross section? Amount of wastewater, slope of wastewater, variation in flow, depth of sewer, static and dynamic load, operation and maintenance. So these are the different cross-sectional flow you can encounter. Okay, these are some of the precautions and standard you need to take into consideration while doing your hydraulics. Okay, you have to be, your pipe has to be deep as to not to hinder traffic. So pumping out of water necessary. So sometimes you need to endure. Laying pipes, control and backfilling. Then other trenchless construction. What is there? So vitrified clay can be used as a pipe material, concrete can be used as a pipe material, bricks can be used as a pipe material, and plastic can also be used as a pipe material. Okay. Over here. Over here. So you can see this is laying of a sewer line made of PVC. So sanitary sewers are usually very small in size. Stormwater sewers are usually bigger in size. Just hold on. Okay. Water supply pipes should be laid above the level of the sewer. Separate sewer, central sewer should be laid above the level of the storm sewer. That's the for infrastructure designer, draftsman. You must make sure that the water, drinking water supply is upmost, followed by the sewer, and followed by him. So this is what a manhole looks like. If you read it, you understand it. No need to go through all of them. Just go through them. I bet you will grab it. It's no big deal. Okay. So we can read all this and understand them. No problem about them. So back to CIA, what I was trying to say. The major equation is the law of continuity, which is more like a Darcy-Weisbach law, which says that velocity is discharge over A. So if you make discharge is formula, you're going to get CA before you now multiply by the safety factor. So the next thing we're going to talk about is the pump characteristics. So all these ones, I'm thinking we just go through them because they are not cast on. This example of what we call outfall. Please, I'll be mentioning, I'm talking about outfall. Outfall is where your stormwater meets your open drain, open river, or open channel. That is your outfall. Please take notes. So this example of overflow where you combine two different sewer, but I don't want to go through all of them. I don't want to go through all of them. I want to go through them because you still go through all of them and understand all of them. So that is all we need to know about hydraulics. So as you go through all of them, you understand what hydraulics is all about, types of pumps and what they are used for. This is a surface pump and the components. Okay. Then you can go as high as Archimedes screw. This is called Archimedes screw. This is usually found in wastewater treatment plants. Why is it so? Because wastewater always carry debris, dirt. So this kind of pump is most suitable for it. So operation point of a pump. Okay, that's all about hydraulics. Any question? So we've done, I think we've done drainage. Yeah.
I think someone's hand is up. I don't know.
Sorry, you say what? Sorry, sir, you say what, sir? Any problem? No, I don't think so.
Okay.
So in urban drainage, there are many elements in urban drainage. You'll be encountering some of them. We have the combined system, we have the separate system. The separate system goes straight to the wastewater treatment plant. This blue line is a storm line. You can see that the storm line will collect water from ground, from farm, and it goes to the open stream. Okay, so the blue line is the open stream passing through this catchment. So in the combined system, or don't worry, I'll use another one. Combined system will combine both of them, while separate system will separate, put them on separately. So let's define some terms that we'll be using in urban drainage system. When you see ACS, it means catchment area. Example of a given point or structure served by a drainage system. So catchment area, when we say catchment area, it simply means an area being served by a drainage line or drainage system or pipe. Then we have ACP. ACP means sum of all paved surfaces of a catchment. So you can have paved surfaces, you can have NCP, which is unpaved. So if you come to a place, there are areas that are paved, there are areas that are unpaved. The paved areas can also be called impervious area. Then the areas that are not paved can also be called permeable area. Impervious or impermeable, same thing. So you should take note of that. Then you have what we call the degree of paving. How far is this place paved? Paved. And that's a function of the area of paved over total area. That will give you the degree of paving. So this is the runoff, the graphical representation of the runoff, what happened during runoff. You see, if there's rain falls, some will wet, some will be lost as drifting, some will be lost as evapotranspiration, some will go into the infiltration. Only a small percentage will contribute to runoff. So what some terms to take note of. Constant rain intensity does not generate constant runoff. Maximum runoff occurs only after initial losses. Wetting, depression, storage, and etc. are covered. Higher your degree of paving, higher degree of paving leads to less infiltration. Therefore, higher runoff. If you pave your house or with interlock everywhere, only small amount of water will infiltrate the ground. It means that the volume of water that will be coming out into the drainage system will be high. And that function, when you combine it with the time of flow, combine with the slope of the area, you come up with what we call runoff coefficient or peak runoff. Okay. The higher the rain volume, the higher is the percentage runoff. So if the rain intensity is much, definitely paved or not paved, relatively, the volume of rainfall will also be high. So the formula for runoff, once again, is you multiply the rainfall intensity by the catchment area by the peak runoff. This arrow underscore D and N simply means the runoff at a particular duration at a particular frequency. While the catchment area is the catchment area of the subcatchment. Then you multiply by the peak runoff. For a given surface, the ratio between precipitation and runoff depends on the rain intensity and varies over time. Runoff coefficient can be given only for certain conditions. We need different values to solve specific problems. Those are English.
Hello. I can't hear nor see anything. What is going on?
So I'm sorry, I was thrown out by the network, but I'm back now. Sorry for that, please. So where are we again? Okay. So we've talked about all this. So now what happens is that when you have different catchments that have different peak runoff, you use what we call the mean weighted average to get the mean runoff. You know, if you are designing, we say Garki, Kado, and they all have different runoff, but within the same district design, then this one might have 0.8, this one 0.6, this one 0.7. You don't just use the average, rather use what we call mean weighted average. And let me tell these engineers, average is deceptive. That is the weakness of the mean. If you remember those days with these statistics, the mean is deceptive, okay? Because the mean does not give you the true representation of the weights of everybody. If I have 5 naira and you have 2 naira, and if I have 5 naira and you have 3 naira, the average is 4 naira. But that is not, it does not reflect that I'm almost times 2 of what you have. That's by the way. But the point I'm trying to make here is that when you have different catchments with different mean coefficients, what you do is to use not the average of the mean coefficients, but to multiply them by their respective weights or by their respective area, size of area, and then dividing it by the total area. It will look complicated to us, but I'll explain it very simple. Okay, when we go to the rational method exercise, some of us will see it. So, but just take note of the word mean weighted average. It is the average that takes into consideration the weight each person is contributing. If you're going into statistics, into data science, into more advanced level of engineering, you will definitely have to encounter this mean weighted average. Okay, average by the weight is a more true representation of what is happening. Okay. Now, how do you get your mean runoff coefficient? How do you get them? Number one, we said is a function of the rain intensity. Then again, we also say it's a function of the surface of the material. Not every material contributes the same level of runoff. Not every material. Some materials, when water falls on them, they will hold the water. Some will release the water and they will come as runoff. So this table shows you different materials and their corresponding peak mean runoff. So for instance, roof is between 0.8 and 1, be it asbestos roof, long span, or any kind of roof, because they don't hold water. So water will just flow out. So that's why it's very high. Gravel is about 0.7. Green roof is between 0.3 and 5. Asphalt is about 0.9. All of us know that asphalt does not like water. So once water touches on it, it goes out. Cobbles, pavement blocks with small gap like interlock is 0.75. Those with wide gap, 0.25. Then grass paver, when you pave with grass, is 0.15. Then if the land is flat, it's about this. If the land is steep, it's about this. So you can see that steepness and the ability to retain water is what contributes to what peak runoff factor you use. This peak runoff, as I said, is just a safety factor. It's just a safety factor that will take care to say that it's not every rain that falls here goes to the drain. Some got lost by infiltration, by evapotranspiration, by wetting, by deep infiltration, and then finally some come out as runoff. So you can see an instance, look at these surfaces. You'll agree with me that not all of them will contribute the same level of runoff. Why? Because they all have a different level of gaps that could take in water. So the question now is, what value of mean runoff should you use? Well, you consult tables. Okay, after consulting table, you also consult the slope. The higher the slope, the higher the runoff. That's just the meaning, what I'm just trying to say. So if you now know that the place you are designing is very steep, so instead of you using 0.7, for instance, you can start to use 0.75. You just increase it upscale it a little bit so you can take care of the slopeness, because a slopy ground generates runoffs easily. So this table shows you, depending on the slope of an area and the degree of paving, you can get the runoff coefficient here, the peak runoff coefficient. So you have class 1 slope, class 2, class 3, class 4. Class 1 are for slopes that are less than 1%. Class 2 are for slopes that are between 1 and 4. Class 3 are for ones that are between 4 and 10. Class 4 are for slopes that are more than 10%. So all of them, if the rainfall duration intensity is 0.225, for instance, and the degree of paving, when we say the degree of paving means the degree of covering of that catchment, let's say it's 50%, then the runoff will be around 0.72. So there are main tables like this I've been countering. So just remember, paved area. On paved areas, their runoff are close to 0. While paved area, their runoff tends to maximum, which is 1. Meaning that anything that comes as water also leaves as water. Okay. The next one you have here is catchment area. Okay, I've explained this before. Okay, we have area of impervious. So what I want to bring out here is that if you once you've multiplied your catchment area by the degree or runoff coefficient, the new area you get is called impermeable surface, impervious area. Impervious area. And that is the real area contributing to runoff. So I've mentioned this before. We've mentioned this before. Okay. So this is what I was trying to explain ab initio. Watch me. Stay with me. We've talked about this before. So let me give an instance now. Combined sewer. The area of the catchment is 100 hectares, but the area of impervious is 45 hectares. It is this 45 hectares that is contributing to runoff. And how do you get 45? You must have multiplied this by 0.45, which means the peak runoff is about 0.45. We use 0.45. So this 45 now is the area contributing to runoff. And the population is 10,000 people. So the water consumption is 150 liters per capita per day. Infiltration water is 5 liters per second. Therefore, and the time of flow, I need to explain that also. Time of flow means what time does it take a water that falls from point A to goes to the outlet, point B, to flow inside the drain at point B. So normally we use time 10, between 10 and 15 as our time of concentration. Please take note. So even if the water falls falls for over 1 hour, we're not interested. Our job is to take the first 15 minutes. Okay. So when you do that, this when you calculate for the wastewater flow, wastewater flow becomes this multiplied by this, then times the wastewater by the safety factor. If you combine it with 5, you get 22.7. So you can see the wastewater flow here is the dry water flow plus the infiltration flow. The infiltration flow here is fixed. And all of them are always fixed. Okay, let's go. Look at another one now. The catchment area is 100, but the impervious area is 0.27. So it is this 27 that contributes to runoff. Okay, so treatment of stormwater. So look at if you want to treat stormwater, use what we call combined sewer overflow, that is CSO, combined sewer overflow tank. So what it does is this, that when this water comes here, it's highly polluted, it will go into this tank. This is a ground tank, like a sedimentation tank. Then the overflow will flow into the open river. This blue line is a river. And the ones that are at the bottom, which are very concentrated, which have settled down, will now go to the wastewater treatment plants, where they will be treated from primary, grid chamber, secondary sedimentation tank, tertiary tank, removal of micronutrients, and then it goes to the effluents. And the effluents still go back to this river. But before you go back to this river, you have improved the deep BOD. You have added oxygen such that the microorganisms in the water have gone down. So separate sewer system. Okay, I've said this before. The stormwater system from the roof, it flows to the open river, but the sewer line goes from domestic wastewater, industrial wastewater. They go through a wastewater treatment plant before they leave and goes into the open stream. The same applies here. Okay, for the combined, you can see that two of them are combined. They are combined until they got to what we call the overflow structure. The combined overflow structure. From there, few of them will go to the treatment plant to be treated before being discharged, while the overflow will go directly into the open water body. I think that's understandable. Combined sewer system, separate sewer system. So for the combined sewer system, there are some. Let me if we read this, we'll understand it. Let's not go through all this. Just really understand it. These are a technical issue. Choice of sewer and what have you. Okay, modify system, just like a combined system. Too much. So, okay, treated this. So, the advantages and disadvantages of the different systems choosing. That's not really necessary. Okay, that's the end. So, any question? We're going to take a 10 minutes break. But that will be after you ask me your question. And for those that have not paid, I think this is an opportunity for you to effect your payment. When we come back, we're going to what we have for today. I don't want to waste our time. We've laid the foundation. We're going straight into rational method. I'm going to rational method when we come back. And this is what we're using, the charts. How to fill these charts. How to develop this chart on your own. Okay. So this is what we're going through when we come back. You all can see my screen, of course. So, okay. Now for the rational method, it is one of the most advanced method for designing sewer and stormwater. And gentlemen, if you can grab it, I will be satisfied. If you can understand these charts and you can develop one on your own, then you have become a guru in sewer storm infrastructure design. Because you cannot do sewer and infrastructure design without these charts. It's not possible. So this chart is more like your calculation sheets. This chart is more like your calculation sheets. So I would like you to, when we come back from break or while we're talking, you can open it. It is called the rational chart. Rational chart of rational method. Please combine it. That is where we are going next. And then we'll be doing one exercise. This exercise here. Okay. That's the exercise we'll be doing. If you can grab it, then, so these are how it will be done. All this in here will now be put them into proper perspective. Then let me see if I have a chart before we go for this break. Let me see if I have a chart of something I've done before. I think I saw something. Yeah, let me see if I have a chart. I see something like rational method modified. Let me check so I can send to us. So that instead of you, so you can start imputing your own in the Excel already. That's the idea. Oh, cool. This is cool. This is cool. Okay, let me share with us. So to share with us, what I need to do is to go back to my folder, the folder I sent to us. I don't know what is in that folder. Please, do you see anything like Excel sheets that have been pre-formatted? And Etuk, you want to ask a question? Your hand is raised. So all I need to do is to just go there, upload it, and you go back there. You go back there and you have it. Okay. Let me put it under this list. I say charts. I'll go here and I'll say upload, file upload.
I just want to ask.
Go ahead, sir.
For some reason, you have not shared the folder with us yet, Elijah. I'm just asking, speaking on my.
I've shared it on the chat, boss, and I asked everyone to go there and download it. I've shared it twice.
On the chat.
Yes. So. I've shared it, and I also said I'm sharing it with the trust that everybody in this class will make their payments. Please, if you know if not make your payments, either you don't know or you just saw the link. Try and make payments. The training is a paid training. It's not free. No free food. I'm sorry. Okay, so I'm trying to. Yeah. Okay. Okay. So let me share. The solutions. No, I want to share the solution, but let me not share the solution yet. That makes some people lazy. So when we finish, and I will now share the solution so that we can now go home and practice it. So everything we are doing today, I'm going to, please, someone should remind me to share the solution. Well, let me just share it. Let me upload it also. Doesn't mean anything. You know, we're all adults. I mean, at this age, you don't need to cheat. I'm sorry, no, when I mean cheat, you don't need to fool yourself and pretend you've known something when you've not known it. So you have to pay attention, learn it. But if you skip or miss something, there are two things you can do. You go back to the solution that I'm going to share with you, and then you go to my YouTube. I will show you my YouTube channel. All these trainings have been done like 20 times. In fact, during this COVID, I've done this training like 10 times. So all of them are being recorded, and this one will be recorded. So if you didn't capture this one very well, and even while waiting for this one to be sent to you, you can go to YouTube after today's class and you watch the whole videos on urban drainage system. They are there online and they are really cool. Okay, so I've shared those things. Let me also share it in our chat box. Please, the payment details is already posted there. If you know you like the training and you want to encourage and keep it going, then you have to do the needful. Okay, it also gives you some level of seriousness. I've seen people who come for training after the day one, they leave because there's no commitment. They didn't pay, they didn't take it serious. And but when you make payment, when you pay for a training, you attach some level of seriousness to the money you've paid. Okay, so rational sheet modified, that download it too. Okay, so I've shared it with us. I will share the solution also, but please don't open the solution yet.
Please, which of the folders are you uploading this now?
The folder that I've shared, the Google Drive, the folder that what I did now was, that's why I share those links. If tomorrow I want to upload a certificate, I'll just upload it inside that folder. Anything I want to do now will be inside that folder automatically.
Yes, I know. I'm asking, is it
Urban
under
drainage,
the urban
under
design?
urban drainage, yeah, urban design.
Okay.
That's where the main thing is. So open it and download it. So we're going to come back by exactly 5. 2 minutes to 5, I'm here. I was having a 10 minutes break for you to take water, drink something, and just make yourself comfortable. It's not good to stay for 3 hours in a place learning something. So I'll see you guys at exactly 5. I'm not going to waste a minute. So even if you finish before 5. So your assignment is go through all these things I've sent you now. Then go through the Excel sheet. Try to make sense of it. 2 Excel sheets, the one that's already filled, and then the one that with the raw Excel sheets and the rational chart sheet. Just try to make sense of it. Play around with it. Thank you. So I'll see us by 5. Take a break. Divide by 100 to divide by the total area. So for instance, now how do I do this now? I have my options. So 1, I'll come here. I will say 63%, which is 0.63 anyway. I can say 63. Multiply by 0.1 plus, that's how to calculate mean weighted average, plus the other one is 12%, multiply by 0.9 plus 20%, multiply by 0.95 plus 5%, multiply by 0.2. Then at the end of the day, you divide everything by 100%. You will get 0.37. That becomes your average. But if you are done 1 plus 9, 0.1, if you are done 0.1 plus 0.9 plus 0.95 plus 0.2. Here is 0.2, please. You cannot get that divided by what? That will be divided by 4. 1, 2, 3, 4. Yeah, divided by 4, which is normal average we do. So sorry, let me take your time. Let me just do it, and just to show you how mean weighted average differ from other averages. 0.1 plus 0.9 plus 0.95 plus 0.2 divided by 4 is giving me 0.53.
0.52.
Yeah, so can you see 0.53 is now the mean average, the mean or the average, but 0.37 is what we call the weighted average. The weighted average gives you a better representation of what should be. Okay, so we've done that. So we'll pass that. Now, after that, you now establish other variables, or what we call takeoff, as we do in design. We're using a 10 minutes storm. I'll explain why. Remember, I told us between 10 minutes and 15 minutes. For the population, for the sewer, we are using a population density of 100 capita per hectare. In other words, we are saying 100 people. 100 people per hectare. 100 people per hectare. That means for every hectare, okay, somebody say about 0.37 serve as a worst case scenario, just my thinking. Yeah, but it will serve as, we want to do that, sir. What you do, you improve on these ones. Maybe you assume that garden is only 0.2%. Do it from here. Thank you. Well, that's a good question. Or when you got 0.37, you say, based on the changing and irrational construction taking place, urbanization of Lagos, 0.37 will be escalated to 0.6. Yes, but that does not change the advantage of using mean weighted average. Okay, now we're using a population catchment of 100 people per hectare. That is what we call population density. Then we are assuming that water consumption is 130 liters per capita per day. We are choosing a peak factor or safety factor, peak factor of 2. Then we are choosing infiltration water of 0.1 per liter per hectare. And for the pipe, we are choosing a pipe roughness or concrete pipe of 1.5. That is the pipe size we are choosing. So these are like establishing your parameters and your assumptions before you commence your design. So what's the next thing you do? In sizing your pipe size is a function of your discharge, your slope, and your roughness. It's a function of your discharge, your slope, and your roughness. Very, very important. So once you can get your discharge, you know your slope, and you know the roughness of the pipe, you can easily go to any chart or any table and design your pipe. And let me say that pipe design is getting the size of the pipe is the most important parameters we're looking at for. I know we're looking for different things in our design, but the output of our design is just for you to get your pipe size. So let us calculate the wastewater flow first. Let us get the wastewater flow. The wastewater flow is now the dry water flow is now the wastewater flow multiplied by the population density, multiplied by the safety factor. You add the infiltration safety flow due to infiltration, you get your flow. So here we say that the wastewater flow, specific wastewater flow is 130 liters per capita per day. Population density is 100 liters per hectare. This A6400 is converting liters per day into liters per second. So 1 day is 24 times 60 times 60. That will give you A6400. If you remember those days in our school, converting day to seconds multiplied by A6400. Then 2 is our safety factor. And then 0.1 is our infiltration flow. Okay, so liters per seconds per hectare becomes 0.1 0.401 is now the quantity of water flowing out of this catchment per hectare. Why this unit is in hectare is that we don't know how many body. We did it based on hectare at catchment level. So if I now want to get the particular flow for any hectare, I'll just multiply it by the size of that hectare. I will get it in liter per second. My end goal is to get my discharge in liters per second or meter cube per second. But 1 meter cube is 1,000 liters. So any question on this, please? Did you understand how this is gotten? If you don't have any question, this can be confusing, but I just hope that it's very obvious to us. If you now come to the storm flow is now the intensity of rain multiply by the impervious area. But the impervious area is the catchment area multiplied by the peak runoff. Okay, let me explain this in the layman's language. Let me explain this in the layman's language. You have a catchment like this, and rain is falling. These are rain falling. Okay, this rain, this catchment has some area like this, and this area is garden, green. Then some areas are residential houses, like this. Then some areas are road. And this road is made of asphalt. Then some areas are football field. Let's say football field. Then some area is markets or whatever. So what we are saying is that the area of this catchment now is AC. But if you now multiply this AC by the runoff, peak runoff, you will now get what we call A impervious, or the paved area. It is that paved area that you need. So I don't know, let's say that this area, this AC now, is equal to 100 hectares. Let's say it's equal to 100 hectares. And our peak runoff, or safety factor, is 0.5. Or let's say 0.6. It means that the area impervious, which is the real area, some people call it the real area, or the area contributing to runoff, is now equal to 100 multiplied by 0.6. And that will give you what? 60. So it is this 60 now that you use. So let's say this unit is in hectares. So it means that the real area now that you use, that are effective, the effective area is now 60 hectares. So that is the import of that peak runoff. The peak runoff is a reducer. It helps you to give you the exact area that's contributing to runoff, because you cannot say all the waters that are falling are going to contribute to runoff. You will be wrong. Okay. Okay. So let's go back. So this is the formula now. So you can see that if you split these two now, you get this. You get the A impervious, where the symbol, the phi, is the maximum runoff. So now, after you've gotten this now, the next thing you now do is to get the stormwater flow. The stormwater flow now, as we said, is the catchment area multiplied by the peak. The next thing you ask yourself is how do you get the design storm? Because if you look at this R, it says that the intensity is a function of the duration and the frequency. So what is the frequency and what's the duration? This table shows you how to choose your D and N, so that when you go to the charts, you know the appropriate D and N to use. Now, if you are designing for rural areas and you are designing for storm, this storm is normal, just normal drain. You use 1 year. If you're designing for surcharge, if you're allowing your storm to surcharge, you use 2 years. If you're designing against flooding, you use 10 years rain. A rain with a return period of 10 years. If you are working on the residential areas, you use 2 years as your return period. If it's for surcharge, you use three. If you're designing against flooding, you use 20 years. If the place is a city center, densely populated area, you use 2 or 5 for your design storm. For your surcharge, it is 5. For your flooding, it is 30. Then underground railway, which is a very critical infrastructure that you don't want it to flood at all costs. If underground railway flood, is a disaster. You use 10 years for your design storm. For your surcharge, you use something above 10, then if it is flooding, you use 50 years. So when we say you use, what do we mean? What we are trying to say is that if you go to your charts, you will see 10, 25, 50, 100. So if you come here, you choose 15 minutes rain and you go up. This is 1 year is about 100. 2 years is about 130. Or bigger. 10 years is about 140. 25 years is about 170. You can see that as the number of years is higher, the intensity of rain is increasing. That means your sizing of your member will also increase because it has a direct proportion. And then 50 years is about 200. The 100 years is about 250. Nobody designed for 100 years. 100 years is too high. If you design for 100 years, your drain size will be like ×5 of what other consultants is. And that is why sometimes the choosing of the return period is a political decision. So that when you go and do your design for your governor or your local government, you design a drain and tell them to use 2-meter drain. They might start laughing at you. But for you and the engineer, you know what you've done. Because you've designed that even in 100 years, the system will not flood. But nobody asked you, because if that place is a rural area, please limit yourself to only what? 2 years. And if you design with 2 years, you should be getting something like, say, 0.9, 1 meter or 1.2, or even 0.6. That is the import of this. That is the idea of this. That is why you need to choose the appropriate one. And as an engineer, as a consultant, you must justify it. You must tell your client that based on this place being, I just told us the experience where we use 0.8. I told my client that 0.8 is too high. But he said, go ahead and use it. And the drains were very massive. The minimum drain there was about 1 meter, trapezoidal, 600 bottom, 1 meter top. That's by the way. So, where are we now? Okay, here. So you can see this is how to get your N. Your D. How do you get your D? D is usually fixed. D is usually 10 or 15 minutes. Quote me anywhere. And that is what we call travel time. Why is it 10 or 15 minutes? The reason is that if you want to get maximum runoff, the time of flow and the duration of the rain must be the same. I repeat, maximum runoff occur when the time of flow is equal to the duration of the rain. It's technical, but with time I will explain it. So what I explained to you is that the time that it will take the rain to flow from where it's coming from to into the drain, if that is the same time that rain is falling, let's say it's 10 minutes, that is when the maximum rain will occur. So in summary, use 10 or 15 minutes. So if you look at our charts here, if you choose 30 minutes, 30 minutes for 2 years is 90. But 15 minutes for 2 years rain is 130. So 90 and 130, which one is worst case? 130 is worst case. So the shorter the duration you choose, the better. But between 10 and 15 gives you something some rains are not up to 10 minutes. So you're meant to choose something less than 10 minutes. But if you choose something less than 10 minutes, the values are not consistent. You can see before 8 minutes, sorry, there are no values. It means the values can be anything. The values can be so high, but you don't use them. Rains, most times when they start, the first 5 minutes is where you see the intensity of the rain. After 5 minutes, 10 minutes, they start going down from a layman's perspective. So that is how to get your N and your D. So what do we do next? I'm moving forward. the next thing you do is the D is also influenced by the slope. So if the slope is less than 1%, you choose either 10. If the slope is less than 1% and the degree of paving is less than 50%, choose 15 minutes. If the slope is less than 1% and the degree of paving is more than 15 minutes, choose 10 minutes. If the slope is between 1 and 4%, choose 10 minutes. Or if the slope is less than 4% and the degree is less than 50%, what I mean the degree of paving, how covered is the area that the water will constitute runoff, choose 10 minutes. So if you look at this table, this criteria, you find out that 10 minutes is more. And that is why we normally choose 10 minutes in our storm design. So if you now choose 10 minutes, what do? You now multiply the area times the runoff coefficient times the catchment area. You come up with a value like this. So now, the concept of rational method. Choose return storm frequency, N. Estimate flow time in the upstream system. Consult IDF. These are the steps you're going to take. Consult IDF curve for corresponding rain intensity. R, a function of D and N. Calculate wastewater flow. So these are the steps you're going to choose. So the first step is choose your return frequency, which I've shown us how to choose it. Depending on whether it's residential area, rural area, and so on and so forth. Estimate your time of flow in the design. Consult your IDF curve for corresponding rain intensity. Required diameter depends on the discharge, your slope, and requires on your discharge, your slope, and your roughness. Okay, the roughness can be fixed. If you're using concrete pipe, just Google online, you see the roughness of concrete pipes. If you're using ductile iron, it's an open domain. If you're using steel, PVC is open domain. So you can fix that one. So what you're not interested in is to find your slope and your discharge. So once you get your slope and your discharge, you are good to go. You are good to design your pipe. Okay, so every other thing here is not too important. Those are checks to check. Okay, so these are the steps, the 10 steps you're going to take to design your sewer system. And let me just show you, give you an example. For instance, for the wastewater flow. Okay, this is the pipe number, pipe A. This is the beginning of the manhole, the beginning and the end. And you know that the beginning and the end, you are meant to put a manhole there. This is the original catchment of pipe A. So if you now multiply the catchment area multiplied by the dry weather flow, and what is dry weather flow? 0.401. This is it. This is dry weather flow. If you multiply this, that's why you see liter per seconds per hectare. If you now multiply by the area, which is the hectare, you're going to get the value for the wastewater flow for this particular catchment. So the next thing you do, hello, you want to ask a question? Okay, so the next thing you do is you multiply the second pipe. Let me go to the beginning again. This is pipe A. The catchment area is 15.63. Here is it. And the wastewater flow coming from all the houses here, or the houses that were built here, is 0.401. That is where I felt some of us were confused. But if you grab it and you understood it and you understand it, then we're good to go. So if you multiply the area, remember what we say about our formula, our universal formula, which holds in every area, is that Q is equal to AV, yeah, which is the area multiplied by the discharge, yeah, of velocity. When I say discharge, it's in meter per second. Why is it liter per second? Because we said that discharge, which is represented as small q, is the wastewater flow of one person, per capita, multiplied by the population density. We don't know what the population density is. It's about 100, yes. So we don't know the number of houses that will be there, but we know the population density. Are you getting it? Then multiply by the safety factor. If you multiply these three things now, it will give you the Q. To give you the Q. Okay? So if you give it the small q, you now multiply the area by that small q. Sorry. It will now give you the big Q. Take note of that, please. So if you now come to our charts here, which is what I am interested in, we just find out before we close for today. Tomorrow we're going to focus on this chart, how to develop this chart. That will be our work for tomorrow. I'm trying to learn the foundation today. The foundation is what we're doing. So if you come to this chart here now, you do A multiply this, multiply by this. This is the catchment area. Multiply by 0.41, it will give you this. This area multiplied by 0.41, it will give you this. This area multiplied by 0.41, it will give you this. So if you multiply the whole area by the wastewater flow coming from those catchments, it will give you the corresponding discharge coming from that catchment. So the next thing you do is you aggregate. If you now aggregate this catchment, you will now find the cumulative discharge. Why are we talking about cumulative? Now, everybody listen and get this clear. When the wastewater is coming from here, the wastewater flow that's coming from here will flow into catchment B. So catchment B will become bigger. Then catchment C will now flow into it at this point. It will become catchment D. It will become bigger. Then it will flow, catchment D, E will now flow into it. Are you with me? It will become bigger again. This catchment now will flow into this. It will become bigger. So as you are going downstream, the flow is becoming bigger. So what is making it bigger is the aggregation or the accumulation or the summation. Catchment A will empty its wastewater into catchment B. Catchment C will empty its wastewater into D, into B, into C. E will empty itself into what? D. D will empty into F. F will empty into H. And that is why, if you do your design properly, as you are going from the upstream to the downstream towards the treatment plant, your pipe sizes will be getting bigger and bigger because the person downstream is accommodating the wastewater flow coming from upstream. The same thing applies to stormwater too. If you are living at the downstream of your estate, the volume of water coming to your house will be bigger than the volume of water from the gate. And that is why if you're designing, if a good engineer does the design, the size of the drain at your own point, who is living down the road, is meant to be bigger. Because as the water is coming from the beginning of the estate or beginning of the district towards your end, because your end or your end is closer to the open drain or the river. So as the water is coming, the tributaries are coming. Tributary A will come, tributary B will come, tributary E will come, and come into this main tributary of B and D. So as they are all coming in, it is getting bigger until it goes into the wastewater treatment plant for sewer or open water body for storm. So that is why if you come to this chart, after you've gotten the respective discharges, you now say A remains A, B remains A plus B, which is give you 8.46. C does not have upstream. So C becomes C, remains C, sorry. Are you seeing it? Then D is now B plus C, B plus C plus itself. And that will give you 15.06. And what does it mean? Huh? Look at it here. A flows into B. B becomes A plus B. D becomes flow from B plus flow from C, and then plus itself. Remember that B is A plus itself. D is now B, which is upstream, C, which is upstream, then himself, D. Then F will now be its own contribution, catchment contribution, plus the two upstream, which is D and E. This is very, very critical. It's very, I understand. If you follow me, you stay with me, you grab it. So look at F now. F is now D plus E plus itself. So if you add 15 plus 5 plus 1, you get 23. And G, what is G? G remains itself. Why? Because G is independent and it does not have upstream. So one of the things we're going to do today when we go back is to study these charts just for wastewater. Please stop at wastewater because this is a combined chart. Study these charts and understand how we came about column 6, sorry. If you understand how we came about column 6, it is the same thing that we did for the stormwater. So here is wastewater, here is stormwater. Everything we did from 1 to 5 is what we're going to do from 7 to 13. It's just the same thing. Are you with me? So that is it. So my recommendation is tomorrow, please, if it's possible for you, print this so that you can hold it in your hand. Print this, and then we will now study the one that we will be able to typeset. You know, I've typesetted one. Where is it again? Okay, rational. Yeah, let's open in Excel. So this is the Excel of this PDF. Now this one is in PDF. So I try to bring it into Excel to make it more let it be editable. So stormwater, okay, this is for stormwater, the same thing. Okay, this is for sewer, it's the same thing. So what do you have here, gentlemen? You can see the length is 500, the slope is this here, convert the slope to percentage, then the area is this, the flow is this. So if you come here now, you see the charts. So this will help some of us. This one say J9 plus I10. So this one is now J9 plus I10. That gives you this. So this is the sewer design. So this is what I want you to practice and see, just take a look at it. So here is constant. So if you multiply this by this, you get this. Then from this, you go to your chart and size it out. So to size this one, this first one says 6.27. So what I will do, I'll go to the charts. See this folder called charts. This chart is you use one that is 1.0, the roughness, because the roughness we were given was 1.5, which is concrete pipe. You choose this one, you choose this. So if you now come to your chart now, this chart is calibrated in liters per second. The flow is on the horizontal, and the slope is on the vertical. This is the chart that you use to get your pipe sizing. Remember, we said with your slope and discharge, you can size any pipe. So here now, you choose the slope and the discharge. So the flow here, you choose it, and the flow here, the slope here, you choose it. So for this one now, we're looking at 6.23. So when I come here, I choose 6.23. I'll go against the slope. From my table, let me see what the slope is.
6.27.
Yes. Then what is the slope? The slope is the slope in per thousand is 5. This one is 5 per mil. I will explain that to you. That slope is in per thousand. The normal slope is what we call percentage. Per thousand means you multiply by 10. So for you to use this chart, anything you get in your slope, multiply by 10. That gives you the real slope. So I'll size it against 5. So when I come here, stay with me. Let me pick up the line. So this is 6. Okay. So when I come here, I pick up 6.2. I'll go against 5. This is 5. It's falling between 2 pipes. It's falling between 2 lines. These are the 2 lines. So this pipe is 100 mm, while this one is 125 mm. It means that any pipe between 100 and 125 mm will serve. But the law says you choose the biggest of the 2, which is what one of us asked me, the one that is on the part of safety. So when you get this, you choose the biggest of the 2. Okay. The reason is that this is a chart. All of us use charts in this. Chart does not give you a precise figure. In fact, engineering is approximation. So, but when you are between the devil and the deep blue sea, you choose, if you are someone that can swim, you can choose the sea, since you can. So in engineering, when you are confronted with two parameters, Y16 and Y12, you know you choose the biggest one, the one that's a part of safety. So in this case, we'll choose 125 because 125 is better. And as I said, the overall principle is that it is better to over-design than under-design. Under-design is bad. So if you now choose this now, the pipe size for that one becomes 125. You go to the second one. Where is it again? Yeah, it can be here. The second one is pipe B. Pipe B is 8. But let me choose a big one, just to one that will show a difference. Pipe D is downstream, it's further downstream. Pipe D is 15.66. So I'll come to my chart now. I'll go to 15.66. What's the slope again? Pipe D. Pipe D is 15.67. And the slope is 2.5. So what I'll do is that I will come here again. And I will choose 15.67 against 2.5. That's where we're going. So this is 15.67. So let's say it's 16. Against 2.5, sorry. This is 2.5. It's exactly 200 mm. So I'd like us to take a look at this. So you can see that this one is now 200 mm. So that is how you do all of them. But all of you just calm down. What I have done today is introduction. I'm not supposed to do, in the previous training, I don't go this far. I don't go this far, but I want to give you a head up so that when you go back today, please, I give indulgence. This is an online training. This is a Zoom training. You need to do part of the work so that when I come tomorrow, each and every one of you should ask me questions. So I've given you an idea. So when I will end this class now in the next 2 minutes, try to play around with this. Try to kind of lay your hands on it and see what this is.